Okay, welcome back. This is the first of a series of videos that I call question and answers, in which I try to address questions that arise either in the chat or by private emails. And I think that they may be of general interest. When I think they could be of interest of all the class, what I do, I make a video about that, illustrating both the question and the answer. And I must say, this time the question was extremely pertinent, and he outlined kind of a sloppy, and if you want to call it a mistake, yes, I think it was a mistake, a genuine mistake I did in my lecture. And to the point that I decided to amend the lecture video and correct it. So you'll see that I re-uploaded lecture 10 with the new versions in which I corrected this small mistake or this sloppy passage, because I think, you know, when you go back to the lectures later on in the course, you might not remember of these corrections that I'm giving you now. So it's good that the material that stays online is correct. So basically, remember, in lecture 10, we attempted to describe the motion of the electron via a standard wave equation. So we were looking for a solution of the equations, second derivative with respect to time, minus second derivative with respect to x. The whole point of the lecture was to show that if you take this form of the equation, you assume the wave function is in a play wave form, then you must come to the conclusion that the energy square is proportional to the momentum square through a constant, whatever it is here. No, I cannot call it x, let's call it a. Okay, so, and this is not what we want, because we know for electron, the energy itself is proportional to p squared over 12. So the overall argument is, of course, correct. This is not a correct wave equation, precisely because you get the wrong dispersion relationship. And in fact, if you look at what kind of systems does obey this equation, typically, if you put 1 over c here squared, that's the velocity of light, and you take this to be, say, the equations for the electric field in the propagating wave, then you get, you know, an equation of the type that the electron, the energy of the photon is proportional, of the wave is proportional to the momentum of the wave through the velocity of light, which is a correct relationship, saying that this is good for photons, but it's not good for electrons. So what was the mistake that I was making on the sloppiness? I was, for some reason, you know, replacing the velocity downstairs with a momentum divided by the mass, which is, of course, true if you assume that the velocity of a particle is the momentum divided by the mass. However, if you do that here, when you drop down the equations, then you come up with an equation that is actually, you know, you get an extra power of p squared down square, and you get energy proportional to p to the fourth, which again is consistent with energy proportional to p squared. So it looks like the wave equation is giving you the right result if you put the p squared down here. True, but this is completely incorrect. And so and the reason is that what this is actually in the wave equation is the propagation, speed of propagation of the wave in particular mean or in vacuum for the light. And it's not something that depends on the state of the particle. The light always propagates at the same speed in space. Acoustic wave always propagate at the speed of sound, and so on and so forth. It's a general property of that wave that doesn't depend on the energy of the wave. In other words, you cannot accelerate an acoustic wave beyond the equation, beyond the speed of sound, and you cannot accelerate light beyond the speed of light or decelerate light. Right? That is a parameter. On the other hand, if I write it this way, this p is not just a parameter, it's a property of the particle. What momentum does a particle have, right? And so I can accelerate or decelerate a particle and changing its velocity momentum. So this kind of relationship like this was not correct. What I could have written here is, well, instead of V naught, let me write m divided by some p naught, where this is a typical or characteristic momentum scale, but there's no reason to do that. So what I did, I replaced the lecture with a new lecture in which I simply make the big point without falling into this little trap. I say that, we want an equation in the form second derivative minus second derivative with respect to space with some proportionality constant, which is basically a generalization of this equation here, times psi equals 0. And if you, apply this, then you come to the conclusion that p squared is proportional to p squared times some constant, which is the whole point of the lecture. So you won't see the wrong derivation anymore online in a couple of hours. And thank you to the students for bringing out this. And if you have more questions, please feel free to ask them either in the chat or by private email. I'll try to address. Thank you. Bye-bye.